Welcome everyone. Great pleasure to have our 17th Marvel Distinguished Lecture. Today we have Professor Feliciano Giustino from the University of Oxford. And Feliciano is actually an EPIs alumnus. In fact, he was an undergraduate at the Polytechnic of Torino. And in 2001 he graduated there. He came here to work with Professor Alfonso Pasquarello in the Institute of Physics. So in 2005, his PhD, and then he moved to Berkeley, to the University of California, in the group of Professor Steve Louie. And he stayed there until 2008, when then he moved to Oxford, to the Department of Materials and to the Materials Modeling Laboratory. And there he did all his professional career, going through the ranks of lecturer, reader, and full professor. Recently, he was the visiting professor at Cornell last year, and I think I'm actually very happy to announce that since 2019 he will become the Moncrief Chair of Quantum Engineering of Materials at the University of Texas, Austin. So congratulations for this, and very happy to have you here.
Okay, thank you for the very nice introduction, and good afternoon, everybody. So today I will try to, so I'm not sure whether I should be behind or in front of this, but I'll try to. I'll basically tell you something about the work we've been doing in the group in the area of electron-phonon interactions. So for those who have never seen me, basically we have a couple of activities. One is materials design, currently mostly on solar cell materials, and another one in electronic structure theory, like many-body perturbation theory and electron-phonon interactions. So today's going to be about electron-phonon interactions, okay? So I'm going to basically give an overview of what we have done and what can be done in this area. So I've been asked to give a very, so basically a talk for a broad audience. So I'm not assuming knowledge in electronic structure theory. And I'm going to start from a quiz, basically. So the question is whether anybody recognizes this gentleman here. And the three hints I'm going to give is that he basically attends his first seminar about quantum mechanics in 1926. It was given by a certain Mr. Schrödinger, and it was entitled Quantization as an Eigenvalue Problem. And just 1 year later, since he was interested about this seminar, he moved to Leipzig to study quantum mechanics with Heisenberg. And 1 year later, he published his PhD thesis with the title Quantum Mechanics of Electrons in Crystal Lattices. So the titles were actually in German, but I'm just translating now. So probably, I mean, you recognize that. That's basically Felix Bloch. He was a Swiss national. He was from Zurich. And he was basically later on the first Director General of CERN. And the reason why I'm putting this picture here is that basically this paper is the paper where basically we started, the community started the theory of the quantum mechanics of electrons in crystals. And that's basically where you can find the famous Bloch theorem that we teach to undergraduates in solid state physics, for example. But the important thing is that in this paper, if you go towards the end, there is a section, and the title of this section is the interaction between electrons and the lattice waves, and the waves, basically the elastic waves of the lattice. So that's basically the first description of electron-phonon interactions, although the name phonon was not invented yet, so he had to call it elastic waves. And what I should say is basically that what he wrote there essentially is still valid today. What we calculate today is largely based on this kind of paper. What happened in the past 90 years is that we basically moved on from descriptive theories of this effect to predictive theories, in the sense that now we can do calculations which are accurate enough to essentially match experiments within a few percent in some good cases, okay? So what I'm going to describe now is what has followed, and in particular, what has followed in terms of ab initio calculations. So since I've been asked to start general, I decided to start from probably the one thing that we all have in common, whether we are experimentalists or theorists or work in different fields. So we probably have all seen the Schrödinger equation for an electron in the hydrogen atom, okay? And for those who have not seen it, it's basically just a differential equation, and the solution is the electron wave function. The square modulus gives the probability of finding an electron somewhere, all right? This capital E is the energy, so that's the electron energy, let's say. So the first term is kinetic energy. The second term is the attraction, the Coulomb attraction between electrons and proton, the electron and the proton, and that's pretty much it. So this is what we call an equation from first principles, meaning that basically we don't have any phenomenological parameters. There are only fundamental physical constants like the Planck constant, the electron mass, the dielectric permittivity of vacuum, the electron charge, and so on, okay? So that's the kind of theories we would like to use to study materials. The only complication is that in materials we don't have only one electron and one proton. We have something more than that. So we have typically many electrons and many protons, many nuclei. So the good news is that the situation doesn't get too much more complicated conceptually. So you basically take the same equation, and you, instead of having one kinetic energy, you have the kinetic energy of every particle here, every electron, every proton. And instead of taking the attraction between electron and proton, you have basically the attraction between each electron and each proton, and then the repulsion between each electron pair and the repulsion between each proton pair. So conceptually, it's the same equation. Okay. The one problem that exists here is that now the wave function does not depend only on one coordinate, but on a lot of coordinates. So this capital psi depends on all the coordinates of the electrons and all the nuclei. So this is basically something that we cannot even store on any medium that we have today, simply because the storage requirements go exponentially with the number of particles. So we're talking about something on the order of 10 to the 40 terabytes for a biatomic molecule. So it's very, very large storage requirements. So that basically means that this equation cannot be solved. The second problem is that there are things like this, which are repulsion between electron pairs. So this is the source of pretty much every evil in electronic structure theory, is what leads to what we call electron correlations, and they are very, very difficult things, and a lot of people are working on these things today. So this is basically hopeless, but this didn't stop people to do, to study these things and to also make predictive calculations. So how did people do? Basically, the idea is to go back to the Schrödinger equation for the hydrogen atom, trying to write basically equation which look like that, but in this case you have a potential which is not just a Coulomb attraction, it's something a little bit more complicated, and this is done within the so-called framework of density functional theory. So clearly I cannot go into details of this, but basically it's a way to replace one equation on a function of many variables by several equations for functions of one variable, okay? And the question then becomes, what is this effective potential? In this formalism, basically, there is a prescription to obtain the electron density starting from the wave functions, and then write down the potential when you have the electron densities. So essentially, we call it density functional theory because this object is a functional of the electron density. So once you have that, you bring it back into the equation, and then you solve iteratively, okay? So that's basically the core engine of every electronic structure code which uses density functional theory. There is nothing too complicated in this kind of formalism, and that's why it has become so popular. So actually this is so popular now that at Oxford in 2010 actually we decided every student in material science should know about this. So basically we wanted to experiment with an undergraduate lecture course on density functional theory. So we started that for third year undergraduate students. The problem we had is that there are no textbooks for that. Most textbooks essentially assume that you already did, you have a master's in theoretical physics. So what we did is to go ahead and try to write a book for the students. So now that's basically the book that we use, and that starts simply from the knowledge of quantum mechanics 101, so the Schrödinger equation for the hydrogen atom, leads to all the way to DFT, basically. So that's to say that now these things are completely, so absolutely popular, and many department of materials around the world are using this kind of, introducing this kind of courses to give people the ability to do these kind of calculations. So the fact that it's popular, however, doesn't mean that they are easy calculations. So that's just a pretty picture to tell you that we basically, most calculations we do are running on very large computers. So that's called Mare Nostrum, is a computer located in Barcelona, and basically we access these kind of computers using, through the well-known PRAISE consortium. It's a consortium of European supercomputers. So you may say actually that this actually is something which is very small compared to what you have here in Switzerland, like Pittsdaint. In fact, this is much smaller, but I would argue that this at least is the prettiest supercomputer in the world, because actually it is installed actually in a church. So if any of you has read the book by Dan Brown, Origin, where it is Robert Langdon, chasing an evil artificial intelligence program, so that the AI program basically is located precisely in this computer in the fiction of the novel, actually. So this is described in that book, and probably there will be a movie soon about that. So remember this picture. Now, this is to tell you that we can do these calculations. We need big computers, and that basically that's the density functional theory for you. But now, what I want to discuss really today is how do we deal with nuclear degrees of freedom. So if I want to discuss electron-phonon interactions, I need to talk about nuclei. So if we go back a couple of slides, basically what you realize that the nuclei essentially appear in terms like this. which is the attraction between an electron and a proton. So that would be the atomic quantum number. And the nuclear variable is basically the position here. So in every DFT calculation that we perform today, these coordinates appear as external parameters, okay? So we are imagining some particles which are located in some positions in space, and they generate this kind of potential. Now, this expression conceals two very big approximations. They have names. So the first one is called the Born-Oppenheimer approximation, and the second one is the approximation of classical nuclei. So whenever we do a standard DFT calculation, we are using these two approximations. So Born-Oppenheimer can be formulated, can be expressed in many ways. The simplest way to say it is that essentially, since nuclei are very heavy, much heavier than the electrons, it may be convenient to factor out the wave function into something which only contains the electrons and something which only contains the nuclei, okay? So this essentially is a way to say that there is no correlation between these two subsystems. The second approximation is motivated by the fact that if you try to plot the wave function of a nucleus in a crystal, you will realize that actually that is a very sharply picked function around the equilibrium positions. So in the simplest approximation, it will look like a lot of Gaussians centered at the equilibrium sites. So since it's a very sharply picked function, people say, well, why don't we replace it by a Dirac delta function? So we then abandon the concept of wave function, and we go to a concept of classical particles, okay? So that's the second approximation. So when we do this, basically, what we are saying is that we are ignoring the correlation between the electronic and the nuclear subsystem, so we are ignoring what we call in solids electron-phonon interactions. So in the next 4 slides, I want to try to convince you that electron-phonon interactions are important in practice, and basically I will try to motivate why we want to study those things. So that's the first example. Maybe it's probably is the least intuitive, but actually is probably the most important. What you're looking at is the absorption coefficient of light of silicon as a function of photon energy. So this is basically the measured absorption coefficient, this line. And I overlay the visible spectrum, visible light. So solar light is pretty much in this range plus in the infrared, okay? Now, what you probably know is that silicon has an indirect bandgap of 1.1 electron volts and a direct bandgap of about 3.3 electron volts, okay? So if there were no electron-phonon interactions, okay, all this absorption here from here to here would not exist. So this would be direct, so essentially 0, okay? So that basically means that if there were no electron-phonon interactions around, one could not make this kind of objects, okay? So silicon is an indirect gap semiconductor, and it absorbs light in the right region precisely because there are phonons around. Second example, probably this is more familiar to the Department of Materials here. This is basically measurements of transport, electrical transport on 2D materials. So that's basically monolayer moly disulfide, and this is bilayer moly disulfide. And the quantity here is the mobility. So the mobility is basically the coefficient of proportionality between the average velocity of the electrons and the applied electric field, okay, in a simple description. So what you can see here is that the mobility basically depends quite strongly on temperature. It changes by about 2 orders of magnitude if you go from 0 to Kelvin to 300 Kelvin, so room temperature. And this parameter is very important. For example, if you design a transistor, that actually determines the switching frequency of the logics, okay? So that's actually quite important and depends on electron-phonon interaction because it depends on temperature. So that's maybe a slightly more fancy manifestation of electron-phonon effects. So maybe we can concentrate on the right-hand side. So what this is essentially is a many-body band structure of strontium titanate, okay, obtained from angle-resolved photoelectron spectroscopy. I will say something more about this kind of structures. But what people were expecting basically is a little parabola here from the experiment. This would be the bottom of the conduction band. So if you dope a little bit, the conduction band bottom of an oxide, you should see a little parabola. So that's what people should have seen. And instead, this experiment gave this object, then a replica here, another replica, okay? So this comes again because of electron-phonon interactions, all right? And then maybe the most spectacular manifestation of this effect, that's, as we know, is superconductivity. So I just put the most, let's say, the most recent record. This is from high-pressure experiments on sulfur hydrides. So basically, these are diamond amyl cell measurements of this oppressed sulfur hydride at something between, so around 150 GPa. So this is very difficult experiment. But the main observation here was that when this becomes solid, it is a metal. And as you cool the system, at some point, the resistivity drops to 0. And the transition temperature in this case is about 200 Kelvin, okay? So this is the superconductor with the highest critical temperature. And this phenomenon is taking place because of electron-phonon interaction. How do we know that? In this experiment, what they did is essentially to perform isotopic substitution. So you change hydrogen with deuterium, the mass doubles, and basically the vibrational frequencies decrease. And as a result, you have a redshift of the critical temperature. That's typically considered the smoking gun of an electron-phonon effect underlying superconductivity, okay? So that's the kind of things that one can see as a result of electron-phonon interactions. And now I would like to tell you how we do calculations about these things. So maybe before proceeding, let me just emphasize one thing, is that when we talk about electron-phonon interactions, there are really two names, electrons and phonons. So the problem is really symmetric. That means that one can study both how the lattice vibrations influence the electrons, but also the electrons influence the lattice vibrations, and both effects are important. And in fact, if one tries to develop a rigorous theory of this problem, one discovers that the problem is indeed self-consistent, okay? So there is really a loop that you need to consider to do this properly. So today, since we don't have an infinite amount of time, I will only concentrate on this side, but if anybody wants to discuss about the other half, I have some interesting data that I can show you if you like. So let's see how this can be done. And since I introduced density functional theory, what I would like to do is to show you actually that we have already all the ingredients to do this, to try, at least conceptually, these calculations. So that's the same equation about, from DFT that I mentioned earlier. And this is basically the wave function of some electrons in, let's say, in some solid. And this is the effective potential that they experience. So let's imagine we start from a solid in the equilibrium configuration, and we define equilibrium as the atomic coordinates given by XRD, okay? At some point, I decide that I want to displace some atoms from their equilibrium positions. So now, instead of displacing every single atom, just to not make the equations too big, I'm assuming that I'm displacing one atom only along one direction. So if I do that, I can maybe, if displacement is very small, let's say a few percent of the bond length, the typical bond length, I can perform a Taylor expansion, and then I will have the potential at equilibrium plus some stuff which is proportional to displacement and the square of displacement and so on, okay? So clearly this is the potential that the electrons feel when there is no displacement whatsoever, right? So what we can say is that whatever is left is essentially the perturbation Hamiltonian that leads to what we call electron-phonon interactions. And I could stop actually to talk at this point because this is it. I mean, there is not much more that we need to know. So what follows essentially is trying to make deductions based on the observation that this is the perturbation Hamiltonian, okay? So if we now try to see what happens due to this, we can basically do what any student would do in quantum mechanics. So you go to the second half of the course and you discover that your lecturer tells you about perturbation theory. So there are some chapters that explain to you that if you have a perturbation, you can do something with that. So let's see what happens in this specific case. So we can use the rules of textbook perturbation theory. So that actually has an historical name that's basically called Rayleigh-Schrödinger, because they are the first people who use this kind of techniques. So the first thing that we learn, probably you will remember that, is that if you take the perturbation and you sandwich it between a given, the wave function of a given quantum state, and you perform the integral, that gives you the change of the energy against state, okay, or that quantum state. If you now take the off-diagonal matrix element, so basically you do the integral between two different states, and you do summations which involve the unperturbed energies, you obtain actually the change in the wave function, okay? That's another basic result of first-order perturbation theory. And now one can do even something more. For example, this corresponds to a static displacement. I can also imagine that my displacement changes as a function of time, for example, like a cosine function, okay? Something which is oscillating. In that case, I should solve the time-dependent Schrödinger equation, and I end up with time-dependent perturbation theory, okay? So the basic result that you find in the next chapter of the quantum mechanics textbook is that in time-dependent perturbation theory, you can calculate the probability per unit time that an electron starting from a given quantum state ends up in another quantum state. And that, again, is proportional to this matrix element, in particular, in this case, to the square of these matrix elements. The other component is a Dirac delta function, which essentially makes sure that the energy associated with this oscillation, so the omega is the frequency of the oscillation, matches the difference between these two states, okay? So this is kind of, some of you may think that this is completely trivial. It's something we see in the third year undergraduates or second year undergraduates. However, what I want to show you now is that, so this actually is what we use to calculate temperature-dependent band structures in solids. So that can be done now. This is something that you can use to study, for example, phonon-assisted optical absorption or phonon-assisted tunneling processes. And this is something that you can use, for example, to study phonon-limited carrier mobilities or conductivities, okay, depending on whether you're looking at a semiconductor or a metal. So what we can do now is to proceed and show you how we use that and some results. But before going there, let me just mention one thing. So when you have a perturbation like that, clearly this change in the eigenvalue is proportional to this displacement, right? So if I choose a large displacement, I will have a big change. So that's clearly doesn't make any sense because it is not very useful at this stage. So we need to, so we can always choose a displacement that makes our perturbation, so our change in energy very large. But that's not what we're interested in. What one would like to know is essentially is an realistic simulation situation in an experiment. What would be this change if you have, if you're trying to follow the dynamics of the nuclei? So one possibility, basically, in this case, is to say, okay, suppose we can define all the initial conditions of the nuclei, and then we let them go. So we can maybe track, their amplitudes, and then we put these numbers inside these equations. That's basically hopeless. Nobody does that, simply because you have a number of atoms, which is of the order of the Avogadro number, so you don't have all these initial conditions. So what people are interested in doing is, for example, looking at thermodynamic equilibrium. So what would be this displacement at equilibrium, okay? So it turns out that in most cases in solids, if you are far from the melting point, you can use an approximation which is called the harmonic approximation. That's basically a change of variables which brings the system from a set of connected springs to a set of independent springs, okay? It's just a variable transformation. So if you do that, basically you end up with a set of springs which are equivalent to a bunch of masses connected to a wall by a spring, and we are looking basically at the average, the thermodynamic average of this displacement, okay? Now, if it's a classical ion, okay, this is quite easy to do. In fact, you may also forget all kinds of theories and derivations. You could write down the average of this quantity like that, okay? For example, you can see quite obviously that the average of the displacement itself is going to be 0, because if it's on a harmonic potential, the number of times the atom is on the left is going to be equal to the number of times the atom is on the right. So in average, it's going to be 0. So the first non-zero term is the square of the displacement. And how do you obtain this function? Well, actually, one can use, for example, the Equipartition Theorem. So you can say that every degree of freedom carries an energy which is kT half. So the degree of freedom corresponding to kinetic energy would be 1/2 u square m omega square. And therefore, if you set that equal to 1/2 kT, you find this expression. So you obtain essentially that the square displacement is proportional to temperature. So if you try to plot it, it's a function looking like this, right? So that's the simplest thing you could do. And that's basically still in the realm of classical nuclei. So we're saying that classical particles vibrating, and that's the mean square displacement. One could do something slightly better, which is basically to replace this object by the quantum nuclear wave functions. And if you do the maths, and these are very trivial maths, you can find them on Wikipedia. It's the first thing you teach to undergraduates when you do quantum mechanics. You basically take the averages on the quantum harmonic oscillator. And the good news is that it looks very similar to this. The only difference is that this is basically the Bose-Einstein distribution. And if you plot these two quantities, the classical would be the black one, and the quantum distribution would be the blue one. So you can see basically that at high temperature, they're essentially the same. They have the same asymptote. They're proportional to temperature. And they only deviate at 0 temperature, where basically the quantum distribution flattens out while the classical one goes to 0. And now one should basically make a distinction here, a precisation, and essentially say, what do we mean by low temperature or high temperature, okay? So that clearly depends on the material. In fact, you can, for example, use a marker. This is a marker. For example, the point where this line, the horizontal line intercepts this, this line here is basically h bar divided by 2. So where h bar omega is the phonon frequency, phonon energy. So that means basically that depending on the system you have, you may be a high or low temperature depending on this or where you are in this plot. Let me make an example. If you're looking at, for example, graphene, the highest phonon frequency energy is of the order of 200 millivolt. So h bar omega half is 100 millivolt. So this is 100 millivolt. That means the room temperature is about here, okay? So graphene is clearly a quantum material in terms of vibrations because the quantum and classical distribution differ substantially. If you're looking at a lead-based perovskite, for example, typical vibrational frequencies are 10 millivolt. So 10 millivolt means that this is 5 millivolt. So room temperature in that case would be about here. So these instances are classical from the point of view of vibrations, okay? So really, where you are classical or quantum depends on the material. That's actually a very important distinction. So that's basically to tell you that we can evaluate these averages, and then we can plug these numbers into these perturbation expansions and see what happens. So first example is how we calculate temperature-dependent band structures. The idea is to take, band structures in a solid. Here I'm not including the wave vector, just to make the notation a bit lighter. Imagine that we have a wave vector there. So what I should do is to basically evaluate this quantity. But what I just told you is that the average of the displacement vanishes in thermodynamic equilibrium, right? So this term is going to be 0. Doesn't mean that there is no change in the band structure. It just means that we need to go to a higher order. So there was a second term in the expansion that I did not carry in the previous slide. Essentially, it's the second derivative of the potential with respect to the displacement. And that is proportional to the mean square displacement, and that is non-zero, as I showed you in the previous slide. Now, the problem is that this is actually proportional to u square if we use first order perturbation theory on the second order term of the potential. I can get another term which is proportional to u square, and that can be done by taking essentially the first order change in the potential to second order in perturbation theory. It's just slightly more complicated. And that leads to an expression like that. And what you can see is essentially both this one and this one are proportional to the same term, and therefore they both have to be included. You cannot exclude one or the other, otherwise you're doing something inconsistent at the level of perturbation theory. And in principle, one could go to U3, U4, and so on, okay? Now, before showing the result, I just want to mention that if you go to the literature, you will find out that this term actually has a name. The name is Debye-Waller self-energy, and this object here is meant to represent a phonon, okay, this wiggle. I will say something more about these diagrams later. And this guy is the Fan-Migdal self-energy. So this is supposed to represent an electron, and this is supposed to represent again a phonon. Okay, that's to say that this can also be derived from the language of Feynman diagrams, basically. And I will go back to this point in a few slides. Let me show you what happens if we use these equations. Let's forget this one for a second, and let me show you what happens if you just concentrate on this bit. You see the denominator is always positive, right? So let's see what happens to this term if you take a standard direct gap semiconductor and assume parabolic bands. Basically here, this summation, so the change of the eigenvalue, if I look at the conduction band bottom, the largest term in the summation are those with the smallest denominator, right? So they will be the ones coming from energies which are very close to the conduction band bottom. But since the conduction band bottom is here, all the other states will be above, and this denominator will be negative, okay? So this is a negative number which increases with temperature in magnitude, okay? So this guy will go down with temperature. For the same reason, the valence band, since that's the opposite curvature, it will have the opposite effect. So it's a number which is positive and will increase with temperature. If you take the difference, you find that the band gap of a solid, a semiconductor in these conditions, has this kind of dependence on temperature. Basically, it's flat at a low temperature, let's say, and then it starts becoming linear at higher temperature, okay? And the important observation here is that if you replace this by classical nuclei, so instead of using the mean square displacement using the quantum harmonic oscillator, we just use the classical nuclei, we will find a straight line, okay? Precisely because of what I told you in 2 slides ago. So what is interesting in this story is that if you do a DFT calculation at 0 temperature, so that's baseline calculation, you just take a system, relax the coordinates, and then you do the band structure. The band structure will yield the properties at this point, okay? So what the experiment is measuring is this point. So this is not the same thing. And this difference is what we call the quantum 0-point renormalization of band gaps and band structures. So let me show you a couple of examples. So this is basically a standard silicon in the diamond lattice. And what you can see basically is the measurement of the band gap. This is anisometry as a function of temperature. And these are our ab initio calculations. So they're not perfect, obviously, because we have problems with correlations in density functional theory. So we had to do some GW corrections, which are not accurate to, let's say, 5 millivolt. But the result is quite good, apart from the offset. And I would like to emphasize that these dots, the blue ones, have absolutely no empirical parameters, okay? So we're not fudging anything. This is basically what comes out of a straight calculation. And you see that basically they follow the experiments quite nicely. That's a similar situation, but for gallium arsenide, it's a similar material. In this case, is a polar material. And what you will notice actually is that the calculations start deviating a little bit from experiment at high temperature. There is a reason for this. We are doing a theory in the harmonic approximation. It turns out that gallium arsenide has a larger lattice expansion than silicon when you go to this kind of temperature, and these effects cannot be ignored, okay? So if you incorporate nonlinear, so basically anharmonic terms in the form of lattice expansion, you would recover basically this line. So that's another kind of subtlety one may take into account. So these are band gaps. So what about band structures? So we can calculate band structures as a form of, in the form of a density of states which depends on the wave vector. So what you need to imagine here is that we are moving along this direction for the wave vector, and for each wave vector we have a density of states which show some peaks here, which are shown as a color code. Okay, so that's what you can obtain when you calculate temperature-dependent band structures. And if you follow the maxima, basically you can track what would be the band structure at a given temperature. In this case, I'm just showing you the difference between a calculation at 0 Kelvin, DFT, and a calculation again at 0 Kelvin, but including quantum nuclear effect. So what you see basically is that the incorporation of quantum nuclear effects decreases the conduction band bottom, increases the valence band top, and as a result, the band gap decreases by about 60 millivolts. Okay? Clearly, 60 millivolts is a small number in this case. So you say, what do you bother doing this? Well, there are several reasons. For example, there are materials like diamond where the change in the band gap coming from this effect is of the order of the half an electron volt. So that's something that is important and has to be taken into account. And there are other systems like topological insulators where you're working with band gaps of the order of 100, 200 millivolts. These kind of changes can signify the difference between something which is or which is not a topological insulator. So that's quite important. Let me show you now the second bit, which is about optical properties. So I promised that this could be used to look at phonon-assisted processes. So why this is possible? So the answer is very, very simple. I'm just going to remind you the expression for the optical absorption coefficient in terms of band structure calculation. So this is the imaginary part of the electric function. The absorption coefficient is proportional to this number. And that's basically given in the electric dipole approximation. So this is basically the dipole operator in the momentum representation, okay? You can see this as let's say you can think of this as an electron-photon matrix element. And this is the Dirac delta function, which tells me that to go from the valence to the conduction band, I need to make a jump which is exactly equal to the photon energy, okay? So that's the standard expression that you would compute to study the electric functions and optical absorption without phonons, all right? So now, if we switch on electron-phonon interactions, the way to do it is basically to take this object and to replace it inside these wave functions here, and here. So if we just modify this initial state, so the initial state here and the final state, including these modifications, these changes coming from phonons, we end up with basically a bunch of terms, which will be basically the original plus the perturbation here, the original one plus the perturbation here. So there are 4 terms to the square, okay? So it will be 16 terms, some will be equal. But the most important thing is that some of the terms will look like that. So there will be basically an electron-photon matrix element, this guy, times an electron-phonon matrix element, this guy. So you start from a valence state, you go to an intermediate state, then from the intermediate state you go to the conduction state. So this should remind you of what you've seen probably in every textbook on semiconductor physics of what we call phonon-assisted optical absorption. So this essentially means that you can go from a state in the valence to a state in the conduction across an indirect bandgap if you have phonons there to help you, okay? So that's basically something you may say, okay, but that's again is trivial. Now, it is trivial from the point of view of basic theory. However, you will be surprised if I tell you that in the literature there are only 2 calculations, so 2 ab initio calculations of indirect optical absorption. So one was from the group of Chris Van de Walle and Steve Liu in 2012, and the second one is from us from 2015, okay? That's to say these calculations are very complex, actually. They're not that easy. And now we are basically in a position to be able to do these things. But the underlying theory is actually very simple. So let me show you how good is the theory. This is basically the same absorption coefficient I was showing you in the introduction. That's basically anisometry, silicon, 300 Kelvin. And this is the result of a calculation that you do within the independent particle picture with the nuclei completely immobile at equilibrium, okay? So you take the crystallographic coordinates of silicon from the crystal structure databases. You do a calculation, and you obtain this result. So those who are aware of the problems of density functional theory will notice that the bandgap seems to be okay. That's because we performed something called a scissor correction to essentially compensate for the fact that DFT underestimates bandgaps. And we do that by using GW perturbation theory, essentially, okay? But that's a technicality to say that we can get something as good as possible, okay? But that's without nuclei, and as you can see, you don't have any absorption in this range, which is the range important for solar cells. So if you were to design, so suppose silicon had not been invented today, and somebody had asked us to screen materials to find good solar cell absorbers, we would basically just pass through silicon and say that's never going to work as a solar cell, okay? And that would be a little problem. Now, if you switch on electron-phonon interactions, you obtain the blue line, and you can see basically that there is an agreement which actually spans 5 orders of magnitude here. And let me say that in this curve, there is absolutely no fudge factor, so we're not changing things to make it look better. This is exactly how it comes out of the calculation without any modifications. So the only thing that doesn't work very well is that here we underestimate the absorption, but actually this has nothing to do with phonons. This is the well-known problem that if you do calculations for silicon, you need to incorporate excitonic effects to correct for this absorption peak. Indeed, if you incorporate excitonic effects, this line will overlap here. But we were not interested in that part, so we can basically just look at this indirect absorption. So that's basically state of the art now. That's what we can do, and that's very general, so it can be done for any material you may like. So today we can do indirect optical absorption quite simply. And now the last bit I want to show is, or the easy part, let's say, is relaxation time. This is basically a very well-known quantity in books that discuss transport in solids. So I told you that we can look at transition rates from time-dependent perturbation theory. That's basically from one state to another state. I can do one extra step and essentially ask what is the rate from an initial state to every possible final state, okay? Just a sum. So that defines what we call the relaxation time. So essentially how long an electron will stay in a given quantum state. So why that quantity is interesting? Well, because for example, if you open any book on solids, like Ashkov and Mermin, and you look at chapter 3, you find the Drude theory of carrier transport. There is something called the Drude formula, which gives you the mobility in terms of this relaxation time. So if you have this number, you can plug it into the mobility, and you can estimate mobility of materials, okay? So that's why this is interesting. In practical calculations, that would be too crude, so you can use it for estimates or for looking at trends, but you cannot use it for predicting properties. So you need to do something a little bit more complicated. So one step up is what is called the Boltzmann transport equation, which basically gives you the mobility tensor starting from the band structures, the band velocities, which are the curvature, the derivatives of band structures, and these relaxation times. Then there is an extra step, which is basically going self-consistent in this equation, which makes things a little bit more complicated, but it's still doable, okay? So let me just show you the results of this kind of calculation, which is something that we added in the past 3 years in our software. So that's basically the mobility of silicon and gallium nitride as a function of temperature. So you can see basically the blue lines are our calculations, and basically the red things are the experiments. And you can see here that the agreement is pretty impressive, both for silicon and for gallium nitride. And I would like to emphasize again, there are no empirical parameters in these calculations. So this is basically a way to say that now we are finally at the point where we can predict mobilities. And this is quite important if you want to design new electronic devices, for example. Just to tell you that we don't do only systems with 2 or 3 atoms. We also did something a bit more challenging. So this is basically, for those who don't recognize it, is let's say the prototypical halide perovskite is basically a perovskite with lead in the center of the octahedra, iodine in the corners, and the organic molecule at in the cages. Okay, that's called methylammonium. This is something which has become prominent in photovoltaics research, and we were interested in looking at the mobility of this compound. The problem, the challenge, is that if you look at the low temperature structure, which is the one where the molecules are not really moving around, so you can talk about a crystal, the structure contains 48 atoms, okay? So we're talking about mobility calculations on 48 atoms, and that's actually very challenging. So this actually forced us to burn a lot of computer time, but in the end we got our data. And what you can see basically is that these are our calculations. So they scale like in experiments, but we overestimate the experimental data. And that is not too surprising because we are only including electron-phonon scattering. So the experiments have much more stuff inside, for example, the scattering by defects, grain boundaries, and things like that. So what we hope is that as the samples will become cleaner, this data will basically creep up slowly towards this kind of theoretical upper bound. But essentially, this is a way for us to tell experimentally that we believe that the maximum mobility you can achieve in these compounds is maybe of the order of 50 to 80 centimeters square volt seconds at room temperature. So if one wants to make transistors out of this, this is essentially the physical limit that they will face. And that basically closes, let's say, the easy part of the talk. And now I know that you're tired, but I want just to spend maybe another 5 minutes to tell you the more difficult things, which are also the most interesting. And what I told you now essentially is how to use concepts from textbook perturbation theory to get materials properties quite straightforwardly, at least conceptually. But there are many instances where these things don't work. Okay? Basically, this perturbation theory will not give you anything meaningful. And the example I want to use actually is from photomission spectroscopy. So that's basically now a very popular experiment now, which is done in synchrotrons or in labs using laser sources. The idea is basically to shine light and extract electrons, then analyze the distribution in terms of energy and angle of the electrons to obtain pictures of the band structure. The advantage of this technique that it really gives us pictures of the complete many-body band structure. So there are lots of effects inside, okay? And the example I want to bring up is basically by the group of Professor Grion here. This is basically a measurement on the conduction band bottom of titanium dioxide. Okay, it's similar to what I showed at the beginning about strontium titanate. So I should say this is basically, I'm showing this because it's the first experiment of this kind and also the cleanest, impressively. The idea basically was to look at the conduction band bottom of titanium, which is an insulator normally, but after doping with electrons. So the way they did doping is by creating oxygen vacancies. Okay. So if you do a band structure calculation and you use the doping levels that they were considering in the experiments, you would obtain something like this, a little parabola, because you're doping a conduction band minimum, right? In the experiments, they don't see a little parabola like that. They see this, then there is some stuff here, all right? So if you try to analyze a little bit the experiments and try to extract information carefully, you will see basically that there is a band here, then there is some kind of replica, and then another replica, and then there are smaller and smaller in intensities. So the reason why I'm saying that is that there is absolutely no way that you can obtain this kind of features using textbook perturbation theory, so Rayleigh-Schrödinger perturbation theory. So this requires more advanced techniques, and that basically brings us to the world of quantum field theory. And that's where things get actually quite interesting. So let me just show you what we do, and then get back to these experiments. So this is something that sometimes people find a bit scary, but actually I can assure you that it's quite basic. There's a bit just some legends about these things, but it's not too difficult. This is the key function of quantum field theory approaches. It's called the Green's function. Okay, it's basically a function of two space-time variables, a position and time, and another position and time, and that's the formal definition. Okay, that's a definition, and it's defined this way by convenience. So what this zero means is basically the ground state of the system. For example, the density functional theory ground state, or any ground state you can come up with, okay, the best thing you can do. When you act with this operator, that's called an electron field creation operator, what it does, basically, it creates a new state, which is the ground state plus an electron sitting at this point and at this time, okay? That is a very well-defined mathematical operation, essentially. And then what you see on the left, apart from this object, which is called the time ordering operator, on the left, you will recognize basically the Hermitian conjugate of what I just described, okay? Just evaluated at another time and place. So what this really is basically a system where you start from the ground state, you add an electron at some point, and then you do the scalar product with the same system, but with an electron added at another point and later time. So in quantum mechanics, when you do a scalar product between two vectors, you are basically asking how much of the first vector is contained to the second vector. Okay, that's basically the probability amplitude of finding this guy inside this guy. That means that's if you square up this number, you get the probability that if you add an electron here at this time, you will find the electron later at this other point. Okay, that's the definition of the Green's function, which is also called the electron propagator. So why this is important? It can be shown basically that if you do Fourier transforms in space and time, you go to wave vector and frequency. Okay. And it can be shown that the poles of this function in frequency space are precisely the energetic excitations of the system. Basically, it's the many-body energy states. Okay? So therefore, if you take the imaginary part, you obtain a function which is a density of states, which we call the spectral density function, aka the spectral function. Okay? The spectral function is basically a density of states resolved in momentum. So if you did DFT calculations before, you've seen many of those. You just don't call them like that. For example, in a DFT calculation, if you have only one band and you're looking at a specific k vector, you will see that the spectral density function, the density of state, is just one state. It's a Dirac delta function, right? Now, if you switch on many-body interactions, like electron-phonon interactions, what happens is that this thing is no longer sharp because the system is no longer a stationary state of the Hamiltonian. You have other interactions. So typically, things deform a little bit, and they start looking like this. So the peak will be shifted, and this change is what we call the quasi-particle shift. The peak is no longer very sharp. We have a broadening. That's what we call the quasi-particle broadening. It reflects the fact that that's not a stationary state, so the electron will decay. It will not stay there forever. And then there is some other structure that is typically signaling some interactions with other things. It could be bosons, other fermions, and things like that. For example, it could be magnons, phonons, plasmons, and so on. So how do we compute these things? At this point, things get a little bit complicated because we need to develop the mathematics to do that. The bottom line is that there is a way to start from Green's functions, which are obtained from density functional theory, and obtain the result that we want by calculating an effective potential, which we call the self-energy. And it turns out that this potential has the same shape of what I gave you at the beginning when I was discussing temperature-dependent band structures. So there is one key difference between what I'm showing here and what I showed you before. Here we keep track of the frequencies of phonons and electrons here and here, and this frequency dependence is what introduces all the strangeness in these band structures. There is a second element, this green object, which is called the vertex. If you ever done GW calculations, you know that there is something called the vertex in GW calculations, which we always neglect because it's difficult. So that's the same thing, but it also includes electron-phonon interactions. It turns out if you want to describe experiments like the one on titanium that I showed before, you must capture part of this vertex, otherwise nothing gets right. And basically, the main point is that you need to incorporate multiple electron-phonon absorption and emission processes in a vertex like this, and that's basically part of some mathematical derivation, which shows that if you don't do that, you basically get incorrect line shapes. So to explain to those who have done calculation like that, that's a bit for the specialist, calculations that don't include this vertex, basically they miss all the diagrams where two lines cross each other, like these ones. As soon as you incorporate this vertex, you basically have these diagrams where you can have emission of a phonon, electron propagates, emits another phonon, propagates, reabsorbs the phonon, and so on. So when you have these crossings, basically you can enable, you essentially make it possible to have line shapes which have the correct structure, the correct energetics, and so on. So the way to do that is called the cumulant expansion method. It's a post-GW method. Essentially, it is done after a complete GW calculation. And if you're interested, you can look at these references, but it's quite technical. And now I want to show you the results. So basically, that's the experiment by Grione's group. And that's for titania. As I said, this is conduction band bottom. And that's our calculation. So this seems like a blob now. I will analyze it in a second, but that's basically what comes out of the calculations, and we are not, again, putting any empirical parameters. What we are seeing basically is our main line here, which is the friend of that, is the quasi-particle band. The first satellite, which is this guy, which is the friend of that. And the second satellite, which should be the friend of that. Okay? So if you try to analyze one by one and compare the energies, actually, believe me, that they actually match with the experiments. And what you discover is that the separation between quasi-particle band and satellite here, and the first satellite and second satellite, is essentially corresponding to the highest longitudinal optical phonon in titanium dioxide, which is about 110 millivolt. Okay? And that's essentially what people call a polaron satellite or polaron replica. Let me try to explain a little bit the physics in a simple way. So if I try to track the maxima of this spectra, okay, I find something which looks like band structure. So there would be a quasi-particle band, then a satellite, then another satellite, okay? That's just tracking the maxima of this function here, numerically. You just follow the maxima. So what this picture means. So imagine you're coming with a photon, and the photon has barely enough energy to extract this electron, okay? So what you find out is an electron, right? So now imagine you come with a photon which has slightly higher energy, maybe this electron plus the phonon energy. So what could happen is that you not only extract an electron, but you also trigger, essentially, you excite a phonon, all right? And if you have a bit more energy, you can also extract an electron and excite two phonons. So how do you visualize that? That's just a cartoon, it's not an ab initio calculation, but basically what is happening is that you come with a photon, you extract an electron, that creates a hole in your material, okay? There is a puddle of positive charge. Titanium and oxygen are 4 plus and 2 minus respectively, so they're ions. So they feel this charge. So they actually feel an interaction with this blue charge, which is the hole, and they will start responding, okay? So there will be forces. So in practice, it's like if you pinch this membrane and the lattice starts vibrating, so there will be a wave of propagating outward from this extracted electron, and this is what we call a phonon, okay? It's not a phonon in the sense of a periodic object, but it's a linear combination of phonons, okay? So the amplitude of this oscillation will be giving you the number of phonons that you have excited. So the more phonons you excite, the higher the amplitude, okay? So that's basically the mechanism that is happening. And the physics is quite simple. So if you want to extract an electron by photoelectron spectroscopy, it's actually, you cannot think that you take out an electron and nothing else happens, okay? So the system is a charged object. There are particles that will interact. So as soon as you take out an electron, other things will start responding to this. And that's exactly the physics that is being looked at here, okay? And what is impressive is that everything is quantized, so you really see these nice satellites showing up. Just to tell you that this is not a single, an isolated case, this has been demonstrated for now at least 3 or 4 oxides. And I just want to show you a recent result on Europium Oxide, which we did in collaboration with a group of Filking in St. Andrews. Just because it's a very pretty oxide with very pretty signals in ARPES. Basically, it's a rock substructure with europium and oxygen, and it is stable under ultra-high vacuum. And it's interesting because below 60 Kelvin, it can become ferromagnetic, and it's a semiconductor, which is also a ferromagnet, okay? So if you look at the band structure, basically, you have the top of the valence band is europium 4F, spin up. The bottom of the conduction is europium 5D, spin up. So the spin down electrons are far away. So these are completely spin polarized semiconductors. So that's why it became kind of fashionable a few years ago, because it was essentially the first fully spin polarized semiconductor, and you can use it in principle for spintronics. Problem is that if you oxidize it, it becomes europium sesqui oxide, so U2O3, and if you go above 60 Kelvin, it's no longer ferromagnetic. So for practical application, it's not going to work, but it's an interesting proof of principle. So here, what the group of Filking did is to essentially dope it with gadolinium. That means that you should be placing some electrons in the conduction band bottom. Then they did the ARPES spectra, so you recognize the oxygen 2p band here, the europium 4F here, and then we would expect to see something here, right? And you don't see anything. But this is quite typical in ARPES. When the signals are small, you don't see much, but you can zoom in. So if you zoom in, you find something here, basically that corresponds to the conduction band bottom, and you find this object. So again, we find a conduction band bottom, which is this object, plus a couple of polaron replicas. So we did calculations for that. So this is basically the same picture in the experiment, and this is our calculation. I don't know if you can see properly, but actually there is a satellite also here. Ours is less basically broad, because we're not including experimental broadening. And also there is a little bit of uncertainty on the determination of how many electrons you have per unit volume, so on the density of electrons. But I would say the agreement is reasonable, and if you take a cut along the, essentially, this k equals 0 here, you will find this density of states, the spectral function for the experiments, and is the calculated one. So, if you consider this as an ab initio calculation without any parameters, it is quite impressive to see that both the energies of the satellites and the intensities look quite similar. So now there is a lot of work going on to this. I don't have time to tell you all the story, but essentially, just to anticipate a little bit, what we discover is that if you keep doping, actually, you discover another quasi-particle there, which is a electron, basically a polaron formed not by phonons, but by plasmons. So that's a whole story there, which is very interesting. And you will find other satellites at different energies, which corresponds to the emission of plasmons in your system. Now, what we are trying to do is essentially to understand what are the implications of these kind of things, for example, in electron transport. We are using to think about bands. So there is an electron traveling to a band. We have a band velocity. But what I'm telling you is that the conduction band bottom does not look like a sharp peak. It's not one band. There is some kind of line shape here, and this has to be incorporated somewhat if you want to do accurate calculations. So that's basically brings me to the end of the story. I just want to say that to recap a little bit, I told you about the optical absorption in silicon, maybe the band gap, temperature dependent band gap in gallium arsenide, mobilities in silicon and gallium nitride, and maybe in perovskites, polarons, satellites in anatase, titanium dioxide, and europium oxide. I guess it's clear that the element in common to all of these things is that they all have some interesting electron-phonon interactions. Maybe more generally, that's the way I like to see the problem, is that these things are really everywhere if you look carefully enough. In some cases, they're important for applications. In some cases, they're not, but there is very much interesting physics to look at. So that's why we like to work in this area. If you're interested in the mathematical details, I'm sorry I couldn't give all the details, but essentially what I did is to collect everything we understand today about these things into this review, and you can see all the derivations there. So all the quantum field theory things, you can find them. They're not something like coming from the sky. It can be just derived step by step, very simply. And all the calculations that we did, that I presented, have been performed with EPW, which is a software we developed in our group. And it's basically designed to do electron-phonon interactions effectively using the maximally localized 1A functions. So this is basically, since maybe 2 years now, is a core module of quantum espresso. We decided essentially to merge because it's based on quantum espresso, and because essentially it's a useful tool that could be used by other people as well. And in fact, now, if you are interested in these calculations, we had a school on electron-phonon interactions last spring. Now, that's not relevant for now because it's in the past. But what we did is to upload basically every lecture, every tutorial on this web page, basically. So if you want a crash course on electron-phonon calculations, basically it should be possible to get everything that I told you today to calculate it in 1 week, at least in simple terms, using these tutorials. So these are the people who work on these projects. Basically, Mario Zacharias was working on the indirect absorption. Samyat Ponce is the main developer of EPW. Carla worked on the polaron satellites and polar electron-phonon coupling. Fabio is the one who developed the cumulant expansion in the group, and Martin worked on the electron-phonon interactions in perovskites. And then there are collaborators like Roxana Margine in Binghamton, who was also a developer of the code, and Phil King and John Riley in St. Andrews for the ARPES on Europium Oxide. And if you allow me just 1 second, I want to advertise a conference that we're going to hold in Oxford next year. Basically, this is going to bring together a lot of people doing ARPES and on correlated oxides, quantum systems, 2D materials, and essentially people who are interested generally in theory and experiments on many-body interactions. So if you're interested in joining, we will be opening the announcement maybe in a week or 2. Okay? So this is it. Thank you for your attention.
Great. Thank you.
I wanted to ask you, the electron-phonon interactions are also important in the cooling of hot electrons.
Yeah.
So some of the perovskites, the nanocrystals, like formamidine lead bromide, they even though they have very mild size condensation, they have very, very slow cooling of the electron. And so could you provide a theoretical explanation why these cooling times, they go into many picoseconds? And
yes.
So that's we have published papers with Singapore group in Nature Communication. And still is a debate why these interactions are not more efficient in cooling phenomena.
Yeah, so basically, I guess, so in this work, basically, so this is mobility. Before getting there, we had to do this other work where we looked actually at the relaxation rates. But that's only for methyl ammonium lead triodide, basically. And this can be computed, I mean, at least at this level, let's say. The limitation we have is that the calculations are done for a perfect crystal, meaning that we, at least in our group, we tend to look at the orthorhombic phase simply because we know where how the molecules are oriented. Okay. The problem that if you go to higher, so to cubic phases or things like that, these molecules are rotating. So these kind of techniques will not work. I mean, even though there are groups trying to use them, that kind of extrapolation is not going to work because we're not talking about phonons anymore. We are basically talking about atoms completely changing their location, and that distorts also the lattice as a result. So that problem probably is best addressed by molecular dynamics simulations like, Philip.
You could use cesium as an AK.
Yeah, that's absolutely. Yeah, I mean, but so the rates that are done, let's say, for a structure which is not, where a molecule is not rotating, can be calculated. In fact, in this paper, we did that. And for the low temperature phase of methyl ammonium triiodide, our calculations were in quite good agreement with the experiment. But they're all in the order of, actually, are quite fast in methyl ammonium triiodide. They are quite, maybe 30 femtoseconds, something like that, at room temperature. So, they match within this kind of theory. And no, we haven't done for meridinium. So I don't know the numerical answer to that, but it is possible now. I mean, essentially, at least when there is a well-defined crystal. Let's say that's the answer.
Thanks.
Thank you for the beautiful lecture. First of all, I have a kind of a philosophical question. In the first part of the talk, you showed a very nice agreement between theory and experiment, for instance, in absorption. And still you do a ground state calculation, while the gap should be an excitation. So why is the agreement so good?
Oh, basically so I think you're referring to that.
Yeah.
So basically here, if you do a calculation with DFT, the band gap of silicon is too small by half an electron volt, but that can be corrected using a technique called GW. Okay. So GW actually, what it does is not to give, let's say, electronic eigenvalues, but really excitation energy. So the eigenvalue we calculate in GW is an addition or removal energy. So it's precisely what you're asking. What we are not including truly here is electron-hole interaction, okay? And that should be done. It can be done. It's more expensive, and that is responsible for this thing here. But that's more about the height of the peaks in silicon. So we didn't look at that because it's in the community is quite well known. So it's a separate problem, let's say. In fact, what we're trying now is to look at the same problem, but incorporating those effects and try to get a calculation with all of this included. It just, I mean, conceptually it is the same, but computationally it is much more demanding. That's the problem, because basically as you put more layers, it gets just dramatically more expensive.
So you show an example of polaron replicas for states which are very close to the conduction band.
Yeah.
What do you expect to observe, for example, in lower line state, for instance, in a balanced band? Do you expect the line shape to get renormalized also there?
Yeah, so basically, I don't have the slides, but that's actually what we did in, basically these things are everywhere, okay? The question is whether you can observe them or not. The problem is that as you go down in the valence, okay, the electron-phonon interactions tend to broaden the states, okay? So the line width becomes very, very broad, and it's larger than a phonon energy. So this thing should exist, but it will be basically embedded in the complete line shape. So in that case, what actually we did, this is actually before even looking at phonons, is to show that if you study the many-body band structures of a semiconductor, and you consider this effect properly, you obtain a replica of the entire valence band coming from the plasmons. So we show that in silicon. So basically you have a bandwidth of 20 electron volts in silicon. And the plasmon energy is 16 volts. So what you find in silicon is basically a replica of the entire band, 16 volts below, actually. And that was actually confirmed by experiments later. So these things should be ubiquitous. It's just that now that we and experimentalists know about this, it's becoming more popular to look at them and to look for them, let's say. Typically, you see what you're looking for. I mean, you may spot them by chance, but as you see here, if you didn't know that there could be this kind of effects, you would not look for that. Okay, so now these things are there and should be observed. So they should be ubiquitous. But basically, what I'm saying is that here you see, if these features are the order of 60 millivolt, here we're talking about something of the order of 1 volt. There's no way to distinguish them. So all these nice experiments actually were possible because people look at very near the band extrema, and there the electron-phonon and electron line widths are extremely tiny. That's why it's possible.
More questions? One, I would say, down there.
How straightforward is to
and calculate phonon-phonon interactions.
So basically, yeah, it is. So phonon-phonon interactions have to do, I mean, so let's say the phonons come from second derivative of total energy with respect to displacements. Phonon-phonon essentially comes from, so that's basically second derivative with respect to displacement square times displacement square, okay? Phonon-phonon comes from the cubic and quartic terms, for example. So you need third order and fourth order derivatives. These are time consuming, essentially. So typically these things, because they scale combinatorially with the number of, with the order that you consider. So people doing these things are those working on thermoelectricity, where you need that for the thermal transport, and they can be done. But at least as far as I understand, they are doable for small systems. You cannot do them for 50 or 100 atoms because you need a lot of calculations. So in those cases, what people prefer to do, to look at, for example, thermal transport, is go via time evolution, molecular dynamics, basically, which could be more efficient for certain things. But in principle, the whole theory could be done in a similar way. It's just the calculation is quite different.
I will close here the lecture because it's also late for everyone. So I thank Feliciano again.